Good day. Welcome to the Physics Exercises channel. Today I will talk about Gauss's law. Okay, so let me actually find myself a pen. Yep, got it. Okay, so Gauss's law. Okay, but I'm going to talk about it in a particular case. So let me first state what Gauss's law is. And Gauss's law of electrostatics states that if we carry out the flux integral over a closed surface, we get something that's proportional to the charge. Okay, and the proportionality constant, 1 over epsilon 0, is a universal constant. Okay. Um, okay, and I'm only going to work in this video on the left-hand side of this equation, left-hand side of Gauss's law, I call it. And I'm only going to address spherical symmetry. Okay, spherical symmetry. Okay, and then we'll put it together. And what I want to focus on is how to do this flux integral. Okay, and let me make some general remarks here. So first of all, Gauss's law is useful when you have a symmetry in your problem. And one possible symmetry you can have in a problem is the spherical symmetry. The other ones that are still manageable to treat with Gauss's law and are usually presented in Physics 101 classes are the cylindrical symmetry and the planar symmetry, and we will talk about that too on other videos. But let's discuss the spherical symmetry, and like I said, only the left-hand side of Gauss's law in this video. Okay, let me actually just mention though for the right-hand side that and I should be a little bit careful here, apologies. What we mean here is Q enclosed. Okay, so let me actually erase that and rewrite it. So the charge there is not the entire charge in your system, it's Q enclosed, which is what we mean by that is that the closed surface over which the left-hand side is integrated encloses some charge, and it's that enclosed charge that is meant by Q enclosed on the right-hand side. Okay, but there are two difficulties that students often encounter with Gauss's law. One is how to do the left-hand side flux integral. The other is what is meant by enclosed charge, but that's going to be in a later video. Okay, so we have a system with spherical symmetry. Okay, so let's restart everything. If we have a system with spherical symmetry, then our coordinate system typically has an origin. Okay, and we would have a charge distribution, and if it's spherically symmetric, okay, let me actually write the fully general charge distribution that we can have. And recall that in spherical polar coordinates, we have not x, y, z as our coordinates, like in the Gaussian, but we have r, theta, and phi. Okay, so we specify a coordinate by first specifying, so let's say we still refer to the z-axis. Okay, so this is the Cartesian coordinate system that I'm drawing now, x, y, z. And here, to specify a point in the x, y, z coordinate system, you specify it as x, y, z, which are all distances along particular axes in particular directions. But in the spherical polar coordinate system, what you do is to specify how far it is from the origin, what angle it makes with the z-axis, and the third angle. So I'm going to try to draw this. So suppose that here's our point. This point is at a distance r. Okay, it makes an angle theta with the z-axis. Okay, and to determine the angle phi, you you make the projection onto the xy plane of where the point is. So there's an implicit vector here, right? The position of a position is by definition a vector. Okay, so you drop a perpendicular to the xy plane, and this angle here is the phi angle. Okay, and now what we mean by spherical symmetry is that the charge distribution depends only on r. Okay, so no theta nor phi dependence. Okay, so that's what we mean by spherical symmetry. Sorry, spelling mistake. Spherical symmetry. Okay, so that's our fundamental problem, a spherically symmetric charge distribution. Okay, what examples can we think of? Okay, so the simplest example one might think of is the point charge Q at the origin. That's obviously spherically symmetric. One way to test whether something is spherically symmetric or not is that to pick any axis and rotate. Okay, so if I pick, this might be my z axis, and certainly if I rotate this around the z axis, and here's the x-axis, nothing changes, right? So if I rotate this charge this way, it's still going to have the same electric field. If I rotate it around the y-axis, it's still going to have the same electric field, and so forth. And any arbitrary axis, I don't know, let me call this the q axis. Well, no, q, we used that already. Let's call it the beta axis, okay? So if I rotate the charge around that beta axis, nothing changes, okay? So the electric field is still going to be the same. Okay, so that's another way to see what spherical symmetry means. Okay, now what I want is, I wanted to say other examples of spherical symmetric charge distribution. Here's another one, a simple one, and one should be able to solve it using Gauss's law. Here's again, I first just sort of I'll draw the coordinate system. Here's a sphere, okay, and suppose that this sphere has a radius, capital R, okay, and it could have homogeneous charge density inside, in which case the total charge is 4 pi over 3 r cubed r. Okay, but in any case, this is also a spherically symmetric charge distribution. If you rotate it, nothing happens. Any charge distribution which is dependent only on r will have this property, right? So all of these are examples of spherically symmetric charge distributions. Okay, now how do we apply Gauss's law? And like I said in this video, I will get to the left side of Gauss's law. Okay, so we'll evaluate the left side of Gauss's law. But first we talk about what is meant by a Gaussian surface. Okay, so what is meant by a Gaussian surface? Okay, so again, here's a coordinate system. I just draw that for reference, x, y, z. Okay, and by Gaussian surface, we mean a surface that we choose. Okay, so it doesn't have to be, it doesn't even have to be related to the charge distribution. On the other hand, an arbitrary surface will not exploit the symmetry. In other words, it will not be useful in doing calculations. Okay, so in this case, we choose the Gaussian surface according to the symmetry. Okay, and I'll just indicate it like this. Okay, now, and this, I'm going to denote the radius of this Gaussian surface by small r. Okay, now it could be that we are doing, we are doing the problem of the sphere with homogeneous charge density and radius r. And in that case, r could be smaller than r could be equal to r could be greater than r. And we will see one in the next video, not this one, how we can actually use Gauss's law to calculate the electric field inside and outside the sphere. Okay, but here, the only thing I want to focus on is how to calculate this, the left-hand side of Gauss's law. Okay, no, in the case where we know that there's spherical symmetry. Okay, and what the thing that you know about spherical symmetry is that the electric field, okay, the electric field, so a priori, the electric field could have three components. Okay, so either we write it in Cartesian Ex, Ey, Ez, but that's not convenient here. So I'm going to write the three components as Er, okay, and it could depend on r, theta, and phi. Sorry. It could, in principle, have a theta dependence, r, theta, and phi. Sorry. This should have been a theta, not a phi. Okay, and it could, in principle, have a theta direction also. Okay, at any point. Okay, a priori, we cannot exclude it, but the symmetry here allows us to exclude some of these things here. Okay, so first of all, since rotating around any axis doesn't cause a change in the charge distribution, we get back to the same place if we rotate it. That's what it means to be spherically symmetric. That means that nothing else can depend on theta and phi either. Okay, so all of these components have at most an r dependence. Okay, but you can sort of intuit that if you have a point charge at the origin, for a point charge at the origin, we only had an r component of the electric field, no theta and no phi component. And that's going to remain true if we add shells of electric charge onto that point charge. And that's the only thing we can do in a spherically symmetric system. Okay, so in other words, what happens is that E, which is a vector with three components, normally, in this coordinate system becomes remarkably simple, because on the one hand, we only have a radial component, and we only have a radial dependence. That's the only thing that we can have in a spherically symmetric system. Now, actually, it's a little bit hard to picture in this case why there's only a radial component of the electric field. Let me give it a shot. Okay, so suppose that I have, let's do it in 2 dimensions, and we can generalize the reasoning to 3 dimensions. So basically, you could sort of build up a charge distribution in 2 dimensions. Okay, so let's say I start with one at the origin, and I put one here, one here, one here, one here. So I'm not building here a spherical charge distribution. Instead, I'm building one that is inside the disk. Okay, and the point is that this charge will have electric field lines going out in all directions. This charge will have one going that direction, one going that direction, one going that direction. Okay, but let's just consider these two. Okay, so if I just consider those two charge distributions, we see that some of them are pointing against each other. Okay, so if you have two charges next to each other, okay, if you have two charges next to each other, these electric field lines are opposing each other. These ones, so this way and this way, they are not opposing each other. Okay, and the point is, this is easier to demonstrate in the case of a linear charge distribution, but you can sort of intuit that if I have if I want to build a disk full of point charges, equal point charges, then what will happen is that if I start putting my point charges within a circle, but regularly, okay, so all within some radius, but regularly, then what I'm going to end up with is only an electric field which points radially outwards, because the other components there are this charge, this part, let's say this charge here, let me put a different color, does have electric field pointing in all directions, but the nearby electric charges will cancel many of those components. And that's why in the end you will get a charge distribution, which an electric field which points radially outwards. Okay, this is not okay. This is actually a difficult to picture in the case of a sphere. The easiest one will be the linear one, and I will do that in one video where I do the cylindrical one. So if you didn't quite understand this, then stay tuned for that particular video. Okay, but for now, let's just live with this, that the electric field has a radial component and it only depends on the radial coordinate. And let's see how can we exploit this to simplify the left-hand side of Gauss's law. Okay, and I will write again Gauss's law. So we have a closed surface and we have the electric field and the scalar product between the electric field and the normal of an infinitesimal normal vector on the surface. Okay, so and now let me actually draw again. So I'll draw first my coordinate system and I'll draw my Gaussian surface, and I'll ask you to consider certain things. Okay, so if I have my Gaussian surface, sorry, that's supposed to be a sphere, and the sphere has radius r, and we established that this vector only has a radial component. Okay, so we can write it using a radial unit vector, but we can easily argue that this vector also only has a radial component. Okay, so if you have a sphere, sorry again, my drawing might not be very good. If you at any point you take an infinitesimal surface on the sphere, okay, the normal to that surface is radial. Okay, so in this case, the area of that element gives you the magnitude of that, which is an infinitesimal. It gives you the magnitude, but the direction of that that normal vector. So let's call that, I don't know. You could, well, actually that's dA. Okay, that's what I call the dA. So for each infinitesimal element, we have on the one hand a radial electric field vector. On the other, so this would be our E. On the other hand, we also have a radial infinitesimal normal vector. Okay, and if we take a scalar product of these two, okay, so like this, what we actually get is E R R dA, and these are scalars, these are just magnitudes, and we have a scalar product of r dot r, which is a unit vector in the radial direction. They are both unit vectors in the radial direction, and they're parallel, so this should be 1. Okay, so this takes the value 1, and that simplifies our Gaussian integral, because if we use this, our Gaussian integral becomes E R R times dA. Okay, now the second simplification is that if you go around the sphere, the radial component, so this is the radial component of the electric field, is not going to change. Okay, neither will dA in fact, but so the radial component, as you know, while we are here, while we are here, while we're here, while we're here, is not going to change. So this simplifies our Gaussian integral, and that's not a square root, that's just something I drew earlier. So this this is a constant, and we can take it out of the integral because constants can be removed from integrals. And what we have is ERR integral over a closed surface of the area. And we know that the area of that closed surface, since we chose it to be a sphere, is actually the area of a sphere with radius small r. Okay, so that's 4 pi r squared. Okay, so that's actually our Gaussian, that's the left-hand side of our Gauss's law. And let's just do it for a simple case, the point charge. Okay, so suppose that, because we know what a point charge should give, right? So if I have a point charge Q, okay, and I choose a Gaussian surface, okay, and the Gaussian surface is distance r, well, Gauss's law states that, Gauss's law of electrostatics says that this integral is proportional to the enclosed charge divided by epsilon 0. And here, this is my surface, right? This is my Gaussian spherical surface. And that spherical surface certainly encloses Q, okay? Certainly encloses Q. But the other thing we know that we actually calculated the left-hand side of Gauss's law. So we can actually substitute our finding, which is up here, and we get that the radial component, whose magnitude varies as r, times 4 pi r squared, is equal to the charge, which is the point charge that we put at the origin, divided by epsilon 0. And from this, we get exactly what we expect from Coulomb's law, namely that the electric field is equal to the charge divided by the constant 4 pi epsilon 0 times r squared. So what we have done is we recovered the electric field that we already knew, but here we used Gauss's law. Okay? Now let me actually outline how you can generalize this to any surface you want. So I will just make a quick argument, because if I had a charge here, Q, and suppose that the surface that I choose around it, let me indicate it by a different color. Okay, so here's a blue color, is not a sphere, but some silly surface like this. Okay, some silly surface. Okay, it's still going to be true that E dot dA is equal to Q over epsilon 0. Okay, it's not only for the spherical surface that we have chosen, which is the convenient one to do the integral, it's also true for an arbitrary surface. Okay, and the way you can convince yourself of this is the following. Okay, so here's my charge, and you know that the electric field of a point charge is Q divided by 4 pi epsilon 0 r squared, and it points in the radial direction. Okay, so the first thing we can write is that the left-hand side of Gauss's law, in this case, is going to be Q over 4 pi epsilon 0 r squared. Okay, then I have my r, and I have my scalar product dA. Okay, and this should be equal to what is, in this case, the right-hand side, Q over epsilon 0. Let's make some simplifications. This integral has a constant Q of 4 pi epsilon 0, which I'm going to pull out of the integral. And I have here r dot dA divided by r squared, okay, and Q over epsilon 0. Okay, let's make some further simplifications. We cancel the Q and the epsilon 0. So I'm going to rearrange this as the following. So I have r dot dA divided by r squared equals 4 pi. Now, what is the problem here? We can't just use the same tricks that we did last time. because r varies. Look at our surface. Look at our surface. Okay, so our surface is no longer a simple spherical surface. It varies. Okay, so as we go around the sphere, as we go around in angles, the distance from the origin where the charge is located. So for this particular element, um, r is something, but for this particular element, r is something else, and those two are not equal. So let's say r is not equal to r prime. Okay, and that's the problem. However, what you can do is build up the arbitrary surface. Okay, so once again, I'm going to draw this. I can't reproduce that arbitrary surface that I did up above, but I'm going to try. So I have some arbitrary surface, and you can do the following. Let's consider, sorry, maybe I'll choose a different color. Okay, so sorry, that's our charge is still there. Okay, so let's choose one tiny surface element. And what we're going to do is our arbitrary surface can be broken down to tiny, tiny little elements. And we're going to assume that each of those elements consists of a small area which is on a sphere. Okay? And this is at some distance r from the origin. Okay, so this small tiny element is on a sphere. And the point is that if they're tiny enough, we can build up an arbitrary surface based on using tiny elements like this, but in such a way that they are on a sphere. Okay, but but this element is on a sphere of some radius r. This other element here is also on a sphere. It's also on a sphere, but this has a different radius. Let me try to create an analogy here, which is a two-dimensional analogy to what I'm doing. Okay, let's say I have a point in 2 dimensions and it's encircled. Okay, so let's say I encircled my point. Okay, let's take another example where I have a point and my point is surrounded by something that's not like a circle. I'm going to try to create this arbitrary shape by saying I take a, let me choose another color, apologies. I choose another. So basically what I'm going to do is try to create this shape by saying here's a tiny little element and this is a circular arc. Okay, and here's another tiny little element and that's also a circular arc. Here's another tiny little element, which is a circular arc. So I'm going to build up this line which encircles my origin using only circular arcs. So this is a circular arc, but the radius, for example, here and here is not the same. Or here's another one where the radius is different. So the radius varies, but these are tiny, tiny little circular arcs. Now we go back to the sphere, go back to 3 dimensions. What I'm doing is I'm building my arbitrary shape up using tiny little area elements, which are on spheres. So within this area element, the radius is constant. But when you go to your other area element, maybe one over here, this will have in general a different radius from the previous one. And what I want you to consider is this expression for a tiny little element. Okay, so what do we have here? We have r dot dA, which is the normal vector, divided by r squared. And the point is that you can easily argue that dA, because we chose the tiny elements out of which we build our shape up, this dA actually is is normal to a sphere, normal to a sphere. The other thing is that we're going to have, it's going to scale as r squared, okay? And then we have an area element which depends on which is an area element, doesn't depend on theta and phi actually, but it originates from the area element in the theta and phi by unit vectors in the theta and phi directions. Okay, so I will just write, I can't call it dA because I used that already. Okay, so let me erase this. But the point is that the infinitesimal, my statement here is that the infinitesimal, sorry, let me erase all this. The infinitesimal area is going to be proportional to r squared. Okay, because look, let's say let's go back to the two-dimensional example here. This is an arc length, it's r d theta. If I go further out, this is going to be proportional to r. So this arc length here is longer than the arc length here. Here it's r d theta. Here it's the new r times d theta. D theta is going to remain fixed. Similarly, when you go on a sphere, okay, the area element is going to be proportional to r squared. So if you have the arc length is sort of the one-dimensional analog of the angular area element that you have on the sphere. And since we're talking about areas, it has to be proportional to r squared rather than r. Okay, so basically what's going to happen, now, the other thing that we know about it is that, sorry, I should indicate this proportionality constant. Maybe I will just write a gamma here. Okay, but the other thing we know about this dA is that because we are using tiny area elements, infinitesimal area elements of a sphere, that it points radially outward. Okay, so what we know is that dA is actually points in the radial direction. It's proportional to r squared. And sorry, this gamma actually has to be an infinitesimal because on the left-hand side I had an infinitesimal and there's nothing infinitesimal yet. So I have to put d gamma, okay, d gamma. Okay, let's put this together. We have that r dot dA divided by r squared, and I think I made a mistake. Oh no, okay, this is a vector, it's indicated. So this is going to be, sorry about that, that's an equal sign, that should be an equal sign. So this is going to be r dot r squared d gamma divided by r squared. And you see that r squared cancels, and this is going to give you 1. Okay, and you have this d gamma, sorry for the writing. So it's going to be d gamma. So basically this element just becomes d gamma. So our integral, okay, so let's go back to what we need to integrate, is going to be, so this actually becomes an integral over all d gammas. But it's not going to depend on r, so there's no more r dependence. Okay? And basically, this is giving you the area of a sphere with unit radius. Okay? On the other hand, I did not use a sphere with unit radius. And basically, my main point in this exercise is that this r squared, that r squared, is going to cancel the area, the r squared, which scales the area when your radius varies as you go around this arbitrary shape. Okay, and so basically this is why Gauss's law holds. even though we can easily prove it for a spherical, a sphere surrounding a charge, it holds for any arbitrary shape. Let me make this a little bit more quantitative by by actually explicitly working out the area element. So here's our coordinate system again: x, y, z. Okay, and I have, that's a radial unit vector, let's say. The theta unit vector goes this way. Okay, but that means that actually if you go down here, say, then your theta, the unit vector in the theta direction, by that means we are increasing theta, is the direction in which theta increases. So down here it would be in that direction. So up here it's in that direction. It's a little bit hard to picture the phi unit vector here, but basically the phi unit vector, you drop a perpendicular onto the xy plane, and that's going to be your phi unit vector. But in any point, so let me actually draw this coordinate system again. So if you have a point which is given by r, theta, and phi, this being the radius, you have, that's the increase in r, that's the increase in theta, and roughly, this is hard to draw, that will be the increase in phi. But at any point, you have a coordinate system which is orthogonal in the sense that all of these vectors are perpendicular to each other. And we can now think about what is the area element. Okay, what is the area element when we are on a sphere and when our radius is constant. So we're not going to increase r. We don't care about this. But what we care about is the following. So here's our point again, and we have a theta vector going this way and a phi vector which is kind of going that way. The precise way to specify the phi vector is by dropping a perpendicular to the xy plane. Okay, and now the point is that what you want to specify is this area element. Okay, so two unit vectors, two infinitesimal vectors, one going in the theta direction, the other going in the phi direction. How do we get an area element out of this? Well, we're going to have, on the one hand, this in the theta direction, what you have is r d theta. Okay, so that's an infinitesimal vector in the theta direction. That's because it's an arc length. Okay, that's your d theta. Okay, that's d theta, and it has some radius. Okay, that's r d theta. Now, what about in the phi direction? In the phi direction, you also have an arc length, so it's going to go like r d phi. But you have to keep in mind that this is a projection of the vector down to the xy plane. And if this angle is theta, then here you need a sine theta to get the proper arc length in the phi direction. Okay, so this would be the proper arc length in the phi direction. And if you multiply these two together, then you get the area element on the surface of a sphere of radius r. Okay, so this is the tiny area element, infinitesimal area element on the surface of a sphere of radius r. And let's just check this. Okay, so let's just check this. What do we get if we integrate the full sphere? Okay, so I have my area element on the surface of a sphere, which I derive to be, well, I can rearrange this. It's actually r squared sine theta d phi. Okay, that's the area element on the surface of a sphere. Okay, and if I do the full integral, watch what happens. So theta goes from 0 to pi, and phi goes from 0 to 2 pi. Why is that? So that's So I have here r squared sine theta d theta d phi. Okay, and I'm going to do this for a sphere of radius r. Okay, so I calculated the area elements, and now I'm going to do the full integral for a sphere of radius r. And you know what you expect, but I just want to show you that this works. But first I want to say why those particular limits on the angles. So you see that theta goes from 0 to pi. It doesn't go fully around because um, um, because if you go fully around in phi, the points that would be on along theta greater than pi. So if you go theta greater than pi, for example, that would be a point. But you can access this point by varying phi. You don't, and if you went with theta greater than pi, you would be doubling this number of points in your system. So you don't want to do that. Okay, so there's a rule that theta is going to be between 0 and pi. Let's write it like this. On the other hand, phi goes full circle. Okay, so phi goes full circle. Okay, so any point in three-dimensional space can be specified by Cartesian coordinates as x, y, z, or radial coordinates as r, theta, phi. But while x, y, z goes from minus infinity to plus infinity, that's your R3 space, your r, theta, phi goes between those limits. So 0, theta, pi, and phi is between, 0, phi, 2 pi. Okay? So now having established this, let's do this integral to finish this video. R squared comes out. The phi is a remarkably simple integral. It just gives you 2 pi. And I'm left with an integral 0 to pi sine theta. And I'll just do this quickly. This should give you a factor of 2. And usually the way it's done is by a variable transformation. So we say that dx is cosine theta, for example. X, we could say x is cosine theta. And then dx is negative sine theta d theta. And if you substitute these limits, you have r squared to pi 1 to minus 1 dx, which gives you 4 pi r squared, which is indeed the area of the sphere with radius r. Okay, thank you very much. So I'll produce other videos on the other symmetries and also to how to put together Gauss's law problems. Thank you very much for your attention.